This is the first video on Chapter 37, Linear Approximations and Differentials. So the first video is going to be on linear approximations, and the following video or videos will be on differentials. Okay, so first of all, what is a linear approximation? Well, the linear approximation is simply the tangent line written in function form. So you take the equation of the tangent line at the point C, f of c, and you write it as a function. So you'll notice the slope is f prime of c, and we're talking about the line at the point that passes through the point C, f of c, with slope f prime of c. And so if you look at y minus the y coordinate is equal to the slope times x minus the x coordinate. So here's your y minus the y coordinate is equal to the slope times x minus the x coordinate. Then you take your y coordinate and you add it to both sides. And then you write your y as L of x. So this is just, again, the equation of the tangent line written in function form. That's what the linear approximation, or sometimes called the linearization, is. So that's what it is. Why do we care about it? We care about it because when you look at the tangent line right here, when the point, so some point x is very close to c, then f of x and L of x are close to each other. And if you look at this, you'll notice that L of c is equal to f of c. So at c, they're the same. If you substitute c for x right here, then you'll have L of c is equal to f of c. But what if x is not equal to c? L of x is approximately f of x. How good of an approximation it is depends on how close x is to c. So L of x is approximately f of x for x near c. What do we mean by near? Near is a relative term, but the closer x is to c, the closer f of x is to L of x. As we get farther away from c, what happens? F of x, it looks like the limit as x tends to infinity of f of x is going to be negative infinity, and for the line it's going to come up here. So the farther we get away from c, the farther the line and the function become from each other, at least for this particular example. But when we're very close to c, f of x is close to L of x. Lines are easier to work with than some of the more complicated functions. So we'd rather work with a line than a complicated function, and the line is an approximation of the function. So we're trading some accuracy here for ease. So let's look at an example. Example 295. Our function is the square root of x. We're going to look at the linear approximation, or the linearization of f at 100. So we calculate the derivative of f. F prime of x is 1 divided by 2 times square root of x. If you want to, write f of x as x to the 1/2 power, and then use the power rule. So we calculate the derivative. F of 100 is 10. That's our y coordinate. F prime of 100 is 1/20. That's our slope. And so we write the linearization. We just have our slope, x minus the x coordinate, plus the function value of the x coordinate. So this is our linearization, or our linear approximation right here. We're going to use that to approximate the square root of 101. So we substitute 101 in to L. So L of 101 is 10.05. Now, the square root of 101 is f of 101. F of 101 is approximately L of 101. L of 101 is easy to calculate. We did that without a calculator. We said L of 101 is 10.05, and that's approximately the square root of 101.